general velocity diagram or the velocity diagram that will be used for both impulse turbine and reaction turbine. Suppose if you are having nozzle here, then the steam enters through this nozzle and comes out through this nozzle. The steam will flow basically in this way, VR1. Okay, this will be its axial component VF1. This will be the absolute velocity V1. Since this is V1, this is VF1, this complete thing will be our tangential component. Since it is in this way, so you have to draw in this way due to vector rule VW1. And since this is V1, this is VR1, so this is small one. This will be your U1. This is nozzle. Suppose nozzle, or it may be, you can consider it as a fixed blade for nozzle for in case of impulse turbine and fixed blade in case of reaction turbine. And this angle will be alpha 1. Alpha 1 is the inlet nozzle angle, and this will be beta 1. This is inlet blade angle. Now, the steam will come or it will strike this moving blade. This is the moving blade. When it strikes the moving blade, see, one thing you have to keep in mind, that this VR1 component will always be tangential to the blade, moving blade. So you can see this line VR1 is tangential to this moving blade, this profile. And if I draw the exit velocity triangle, if I draw the exit velocity triangle here, this will be your VR1, sorry, VR2. This is 90 degree. This will be your VR2, okay? This will be, sorry, VR2, this will be your VR2. This will be your V1, V2. This will be your V2. This will be your VF2. And this is VF2, this is V2. So, and the direction will be in this way, okay? So, this will be your VW2. This is tangential component of velocity, absolute velocity. This is V2, this is VR2. So, this small thing will be your U2. Now, this is called inlet velocity triangle. This is inlet velocity triangle. This is outlet velocity triangle. will be your outlet velocity triangle. Now, one thing you can keep in mind, see, the steam is coming through this nozzle in this way, and it will flow and it will glide this blade. This is moving blade basically. This is your moving blade, okay. This is your moving blade, and then it will come out from this moving blade in tangential direction, that VR. This is VR2. The tangential direction will always be your VR2. Tangential to the blade will always be VR2. Remember, this angle will be beta 2. This angle will be alpha 2. So this is your outlet velocity triangle, and what will happen, since the velocity in this way and this, and the velocity going out from this blade is in this way. So what will happen? It will cause the blade to move in this way. The blade is moving in this way. The profile of this blade is like this. The profile of this blade is like this. It's a, since the flow or the motion of this blade is opposite to the motion or the direction of this blade, since the blade is in this way, but the flow is in this way. So this is actually a diagram for backward curved wind. What will be the forward curved blade? If I draw in this way, since the blade is moving in this way along the direction of flow of the steam, and this profile will be forward curved blade. Forward curved blade. You cannot predict every time by staying away from this turbine. How will you determine whether it's a forward curved blade or is a backward curved blade? There is a simple way. You just remember, if beta 2 is greater than 90 degree, then it's a case of forward curved blade. And if beta 2 is less than 90 degree, then it's a case for backward curved blade. Remember, this beta 2, this outlet blade angle. If the outlet blade angle is less than 90 degree, then it's a backward curved blade. If outlet blade angle is greater than 90 degree, then it's called a forward curved blade. And if beta 2 is equal to 90 degree, then it's called radial blade. Beta 2, if it is 90 degree, then it's called radial blades. Okay. I will give you some terminologies so that you will be able to solve questions, some tricky questions in properly. But see, this is the velocity, inlet velocity triangle and outlet velocity triangle. But you know that since it's a turbine, here the U1 and U2 will be same. U1 and U2 will be same. Whether it's a whether it's an impulse turbine or reaction steam turbine. Whether it's a impulse steam turbine or reaction steam turbine, in any case U1 and U2 will be equal. If U1 and U2 are equal, in that case we can draw a combined velocity triangle. How will you draw the combined velocity triangle? Since if U1 and U2 are equal, just superimpose these two portions, okay? Superimpose these two portions and then you will get the combined velocity triangle. So how it will look? See, these angles will be your 90 degree. This will be your VF1. This will be your VF2. This will be your V1. This will be your VR1. Just I am combining these two, okay? These two diagrams. So this will be VR2. This will be your V2. If this is VR1, this will be your beta1. If this is V1, this will be your alpha1. If this is V2, this will be your alpha2. This will be your beta2. Okay. Moreover, we can see this is VF1, this is V1. So this will be your VW1. This will be your VW1 completely, and this will be your U. U means the mean velocity, mean speed, mean blade speed, and that will be common to both the triangle U. Then this is V2, this is VF2, so this will be your VW2. Now it's okay. Now one thing you have to look in this diagram, this is called combined velocity triangle. So in this diagram you can see this VW1 is in towards the right while VW2 is towards the left. They are in opposite sense. They are in opposite sense, and we know from the Euler work done, or Euler work for turbomachinery, what it says? It says VW1 into U1 minus VW2 U2. This will give you the specific work. Joule or kilojoule per kg, whatever, depends on the units what you are taking. So in this case, in this current situation, this U1 and U2 are equal. So VW1 minus VW2 into U. But if you see VW1 and VW2 are in opposite sense. So what will happen? This VW2 will be negative, and negative it will cause positive. So it will be VW1 plus VW2 into U, and this will give you the Euler work or the work for this turbine, the work produced by this turbine. Okay. So you have to keep this thing in mind. And this is the velocity triangle, combined velocity triangle. So this is common for both the impulse turbine as well as the reaction turbine. You know some of the terminologies regarding turbine, okay? Steam turbine. First, going with degree of reaction. just it is represented by R. So what is degree of reaction? Degree of reaction basically R, it is given by enthalpy change in rotor. Rotor means what? Moving part. So enthalpy change in rotor or moving part, moving blade, whatever it is. You can say moving blade. To total enthalpy change in one stage, or the enthalpy change in stator or fixed part or fixed blade plus enthalpy change in rotor. And the stator and rotor together it will form a stage, one stage. So the enthalpy change in stator plus enthalpy change in rotor, basically this is the enthalpy change for one stage. Enthalpy change in rotor plus enthalpy change in stator together is given by Euler work. This will be equals to the Euler work. Okay. Euler work, next we have seen that here in this case it will be VW1 plus VW2 into U. If it's a backward curve blade, and we generally use backward curve blade, this is applicable for backward curve blade, remember, I have shown you. And this whole expression is also equals to VR2 square minus VR1 square by 2 plus U1 square minus U2 square by 2 plus V1 square minus V2 square by 2. This complete thing is also equals to sum of these three parts. Basically, this part is basically called static, okay, and this part is basically called dynamic. Enthalpy change in rotor, if I write enthalpy change in rotor, okay, enthalpy change in rotor, this is basically this static part, this part. So this will be VR2 square minus VR1 square by 2 plus U1 square minus U2 square by 2. So this is the enthalpy change in rotor section. So if I write degree of reaction, it will be VR1 is my part, VR2 square minus VR1 square by 2 plus U1 square minus U2 square by 2 upon VR2 square minus VR1 square by 2 plus U1 square minus u2 square by 2 plus v1 square minus v2 square by 2. So this will be the degree of reaction R. So if you convert this, or if you try to simplify this for impulse turbine or whether reaction turbine, you will get a simplified equation. Okay, you will get a simplified equation, but I will urge you to not to remember those equations. But if you remember this form, in this form, degree of reaction, it will be very useful to solve problems, any problem from basic, because this is the basic formula for degree of reaction. If you try to simplify, I have already told you how to draw the velocity triangle. Let me draw it again. V1, this is VR1, this will be your VR1. This will be VR2, this is V2, this is VF2. This is VW2, this is your U2, this complete thing is your VW1, and this small thing will be your U1. So from this, if you apply some geometry and trigonometry, then you will be able to convert this expression you will be able to convert this expression into generalized form, and you can remember that form if you want. Vf upon 2u cot of beta 1 minus cot of beta 2. This will be the generalized equation for your degree of reaction. Okay, this Vf, remember, in any turbine or in any compressors, we used to keep Vf as constant. Vf means Vf1 is always, we used to try to keep Vf1 is equals to Vf2 in any turbine or any compressor. This is always applicable. And in this case, U1 is equals to U2 is equals to U. In this case, maybe it may not be equal, U1 and U2 may not be equal, but I am taking U1 and U2 to be same. So, if you use this, these two things and this trigonometry, apply trigonometry to this velocity triangle, you will land to this expression. You can remember this expression because it will be very useful to solve the problems, objective type of problems directly without solving. But like for subjective paper, you can use this concept. This concept is always applicable. In anywhere you can apply this concept. This formula, if you remember, this formula for R, this is always applicable. But this formula is applicable only for steam turbine. only for steam turbine. Okay, this power. So this is for degree of reduction.